So, what are we going to do today? We will explore time sensitive networking in an avionics environment. Why is it important? And a comparison of ARINC 664 and the IEEE 802.1 DP avionics TSN profile. Understanding this will assist in our discussion of verifying your new TSN enabled device and the various TSN protocols. So, let's look at a short agenda to see what we will review. First, we will look at what is TSN in general? Then how does it work? We have a few of the profiles included in what may be an avionics standard. Building on these profiles, we will compare ARINC 664, which is another Ethernet-based standard similar to TSN. Then we will talk about your endpoint device and how to verify the various profiles, time synchronization, scheduling, traffic shaping, redundancy, and finally, I'd like to know your thoughts and ideas on verification. TSN was originally conceived to use the Ethernet infrastructure for applications that require deterministic or time-sensitive data handling. Everything from audio-visual systems, SCADA, or supervisory control and data acquisition systems, building automation, and vehicle systems. Now we are seeing use in the aerospace and space arenas. Common requirements for these systems include high availability, guaranteed message delivery, rapid response times, consistent response times, precise timing, and synchronized actions across the network. The basic goal is to prevent dropped frames and allow deterministic traffic. How it works is through scheduling, time synchronization, and calculated bandwidth and latency. As we all know, IT networking has no sense of time, so no sense of synchronization. TSN depends upon a master time, so all nodes have the same understanding of time. This is the basis. This allows everything to be coordinated. Once this is understood, scheduling can happen, path definition and fault tolerance can happen. TSN enables very low and guaranteed packet propagation latency, time-aware scheduling and queuing, time-coordinated forwarding, and frame preemption. It offers very high reliability with zero congestion loss, resource reservation, and seamless redundancy. Let's take a look at some TSN in action. What we have here is a demo we set up with our hardware passing video streams so we can actually see the result as opposed to measure them. We have two pieces of our hardware configured as endpoints. One is publishing the data, the other is subscribing. They both have additional UDP traffic along with the video streams. The one on the left does not use TSN, while the one on the right does. Let's play the video of the two systems and compare. So you will see two different systems set up, all looking at one green ball. You can see some traffic in the background. The video on the right seems to be in real time. The one on the left has latency, is a little jittery, and doesn't seem to be what we need in a deterministic system. So let's start with the time part of it. 802.1 AS. In general, TSN assumes that all time-sensitive elements are synced to a PTP synchronized clock. There needs to be a common time reference. AS defines how TSN ports and switches synchronize their clocks with other network clocks so that the sender and receiver have a shared understanding of time. It uses a defined profile from IEEE 1588. This profile standardizes the use of multiple Grandmaster clocks, as well as the possibility to make multiple connections to these Grandmaster clocks for redundancy and failover. It also defines support for multiple clocks, local 1, local 2, local 3, synchronized to different masters for different purposes. And of course, redundancy. Two active Grandmasters, each transmitting two copies of their clocks using separate paths. Redundancy is definitely an important attribute for avionics systems. Now that we have a common understanding of time, let's look at some scheduling options. 802.1 QAV is also known as the credit-based shaper. Originally for AV or audio-visual targets, the goal was for a guaranteed latency around 2 milliseconds and some kind of control for guaranteed bandwidth. The timestamps needed to be synchronized for media coordination. This system spaces out frames to reduce bursts or bunching. A frame is only transmitted when its credit is not negative. This schedule has user-selectable credit gain and credit loss curves. Frames can be kept waiting until they have enough credit. This prevents starvation of low priority traffic by elevating quality of service priority. It doesn't guarantee timing, but guarantees delivery over best effort traffic. It guarantees bandwidth, which in turn reduces latencies. You can see the effect of less bunching and more regular traffic. So an improvement on AV is the time-aware scheduler, or 802.1 QBV. All nodes need to be synchronized to a highly accurate clock. If you recall, AS is what we just discussed. BV has dedicated time slots, so it can avoid interference from lower priority traffic. These time slots can be thought of as repeated fixed length windows. Typically, there are 8 different priorities implemented. All devices are aware and share the same time domain. They must agree on the windows and gates, and a cycle duration and rate. Endpoints know when the traffic should arrive. It adds time gates on each queue on a port. At specified pre-programmed intervals, a port's lower priority queues can be blocked so that higher priority traffic can pass through unimpeded. It delivers the lowest possible latency for a stream all of the time. By timing the release of packets, control applications can accomplish their tasks. Switches typically implement CH, cyclic queuing and forwarding, so that latency can be measured and traffic can traverse the network. Even non-TSN traffic is gated and is released in time slots, which can result in bursts of traffic that belong to a longer stream. This system can be somewhat inefficient with bandwidth as the windows or gates are sized to the largest packets, even if the actual packet is less and doesn't use up all of the available bandwidth. Here is a picture of 2 cycles with gates. Notice the guard bands. TSN puts these in front of time-critical traffic to ensure the previous traffic is finished in enough time and ensures no new traffic is started. This also can affect bandwidth. 802.1 QBU deals with how queues determine when they can borrow someone else's time window, how the owner takes the window back, and how to stop and later complete the frame that was preempted. It supports one level of preemption, where a higher priority frame can interrupt the transmission of a lower priority frame. When the higher priority frame is done, the lower priority frame continues where it left off. Fragmented frames must be completely reassembled at the link's receiver before they can continue through the bridge or end node. This can improve latencies, and it can improve bandwidth if used with scheduled traffic. As seen by the diagram on the left, pure time shaping only opens one queue gate at a time. With frame preemption, looking at the figure on the right of the diagram, if the queue whose turn it is to transmit, for instance, class 1, doesn't have any data, another queue, class 2, can start transmitting. However, if data suddenly appears on class 1, it can preempt class 2, which is what we see. Class 2's frame transmission is terminated instantly regardless of the frame boundary, and class 1 begins transmission. This results in optimal bandwidth utilization of background traffic for time-aware shaping and low latency communication in non-scheduled networks. Here's another look at it. Again, notice the guard bands ensure that there's enough time so that the critical traffic is started on time. Another profile is 802.1 CB, and it's also known as frame replication and elimination for reliability. It solves the problem associated with CRC errors, broken wires, loose connections, in various network topologies. Time-critical frames are expanded to include a sequence number. These frames are replicated and each copy follows a separate path in the network. At any merge point in the network where the separate paths join again, duplicate frames can be eliminated from the stream. However, replicating at the source and eliminating at the destination only protects against a single network failure. FRARE allows configuring replication and elimination at intermediate nodes as well. Here's another graphical example. Those squiggly paths are meant to show that they get to the end going through different hardware and much different paths. So what about ARINC 664? How does it work? ARINC 664 is also Ethernet based, that's true, but there is no concept of time. Instead, they use the concept of bandwidth allocation gap, or BAG, to achieve determinism. The BAG is a transmission slot of configured duration, during which time the end system may send traffic for a specific virtual link. Each slot or window is allocated at 1, 2, 4, 8, 16, 32, 64, even 128 milliseconds. A good way to think of it is that a window is a time slice to get the bandwidth, similar to a combination of 802.1 AV and 802.1 CB. Each virtual link has a jitter limit, defining how long after the start of the BAG a transmission can start. Typically, there are two priorities, and within each virtual link are sub-VLs that add onto the packet in a round-robin manner. To adhere to its BAG limit, end systems perform egress traffic shaping, modeled after telecom's asynchronous transfer mode, or ATM, token bucket scheme to schedule their transmissions. Switches perform token bucket-based traffic policing, dropping traffic on VLs where the BAG limits are being exceeded. They are the police to remove the bad actors. This is all done without timing or synchronization. The combination of outgoing traffic shaping and incoming policing provide the foundations for determinism in an ARINC 664 system. So what are some of the differences between the two? Well, as we saw, ARINC 664 is optimized for bandwidth by limiting and defining bandwidth bags. It uses up all the bandwidth and assures no hogs. It uses predefined bandwidth and the size of the packets. ARINC 664 is a higher level protocol defining layers 1 through 6, all the way up to the presentation level. TSN defines only layers 1 through 3 to the network level, but not what is delivered within the packets. TSN is optimized for latency, not for bandwidth. So now, instead of designing an ARINC 664 system, you are now designing and building and verifying a TSN-enabled device. Let's talk about the endpoints in the diagram. For example, some avionics or a mission or flight computer. A new device with a new digital backbone. How can we verify its operation? In avionics, there cannot be a single point of failure, so we need to test all the failure modes we can. The determinism, the time synchronization, the redundancy. It really comes down to the packets. What happens when there is babbling or silence? What happens when there are unexpected packets or damaged packets? If we take a look at time synchronization, for instance, what happens when there's a changeover, when one of the grandmaster clocks is disconnected or not getting a signal? As a grandmaster ourselves, we have complete control. We can change all aspects of time. No time, time jumps or shifts. How does your device handle that? What is going to happen inside of your control system? We can change the synchronization or make it not synchronized. We can change the profile for PTP. Everyone needs to be using the same profile. If we change the profile, we can probably drive a different frequency. Assuming time synchronization is working, we can look at scheduling next. One question to be answered: does your endpoint test with a switch or is it direct? A TSN switch also handles many of the error checking and scheduling. So let's assume you are either testing an endpoint directly or the switch itself. Since the scheduling is so important in TSN and control systems, proper testing should include modifying or violating that schedule. Try sending an expected packet late or not at all. How does your device handle that? Another good test is a packet that exceeds the gate length. Again, this would normally be handled by the switch, but really you are trying to look at failure modes in your device and not that switch. In 1553 testing, we often are used to simulate babbling on the bus, an undisciplined device. We should be able to simulate the same in a TSN system. What does it do to your device? How is it affected? A raft of packets outside of the schedule, using up more bandwidth than allowed. They look like good packets, just too many of them. And of course, simulating all traffic outside the TSN managed traffic, trying to overload the system or interfere. This is exactly what TSN was meant to help with. Traffic shaping can be used in conjunction with scheduling, or it can be utilized or tested on its own. Some of the basic tests include packets that are too long for their period or packets that are never sent. Again, let's define that we are testing with a direct connection to simulate the failure modes. Another good test is too much high priority traffic that uses up all the bandwidth, barring other packets from getting through. How does your device handle that? We should also simulate partial packet loss by creating a small gate and killing a partial packet. Assuming there is regular traffic, you should try dropping a preempted packet. Your device should be expecting it, but it doesn't arrive. Now what? More stress testing can include misshapen traffic. Traffic like low priority packets requiring high bandwidth or high priority packets requiring low bandwidth. A very important part of most systems, if not all systems, is redundancy. BR is the redundancy profile. Every node should be able to reassemble the stream if called upon, including the end node. A single point of failure returns if the end node has only one connection and one stream of packets. So both streams should be connected to your end node. Obvious tests include elimination of a path, but you should be able to accomplish this programmatically with your test device, as well as dropping a packet or frame, or maybe even one on both paths. Another good test is to act as an end node without the BR profile. What will your device do with that? If you recall, the BR profile adds a sequence number onto time critical packets. Good tests include sending the wrong sequence number on a packet or even on one of the replicated packets. Do you have complete control of the TSN network? Do you have complete control of these packets? Or are you depending on every node to do its job? If one fails, will you be ready? So thanks for your time. I would definitely like to open this up for questions. I really am trying to learn what more of the verification everyone out there is using. I am joined by Austin Turner and Alex Ivchenko, who have implemented this capability on our platform. They are more than happy to answer any of your questions. Without Alex or Austin, both this webinar and TSN itself on our platform would not be possible. So let's hear your questions and ideas.
Great, thanks, Erik, for that. Really interesting presentation there. Am I right in thinking this is the kind of solution that's needed as kind of aircraft and drones and things like that become more autonomous and need to, their timing becomes that much more important? What's important, the flow of data increases. Is that the kind of situation we're looking at here?
Certainly for autonomy as well as regular human-based control as well.
Okay, great. All right.
We have been learning that the new digital backbone for many avionic as well as ground-based systems will be TSN. So all that'll need to be verified.
Okay, cool. So we have one question so far. Thank you. That is from Les Kronkovich. I think that's how I'm going to pronounce his name. So that should be coming up in the published feed now. Les would like to know how do each of these systems deal with latency created by connectors, connectors, and more connectors? I don't know if Alex or
Yeah. Yeah, I'd like to clarify what connectors mean in this regard. Are you talking about time on the wire, or are you talking about latency introduced every time Ethernet packet jumps from a switch to a switch?
Yeah, why don't we assume that it's the latency that is added when it jumps between switches, then back onto another endpoint?
Well, if we talk about latency introduced by TSN, so what happens every time a packet, for example, if you're using .1 QBV mode of operation, so it's basically time-aligned, time-aware scheduler, every time a packet passes a switch, it's delayed by 1 cycle. The cycle time is programmable for all switches, and for certain VLAN, for certain traffic, it's the same on every switch. For example, the cycle time is 100 microsecond. So every time a packet passes through the switch, it will be realigned to the next 100 microsecond window. So in one regard, yes, the traffic will be delayed the more switches it travels. But on the other hand, the traffic jitter will be kept to a minimum, so the packet will arrive exactly on the time slot it's supposed to arrive. Does it answer your question?
He's written here mechanical wire connectors. I'm guessing your answer is still relevant with that add-on there, Alex.
Well, on the connectors, if you compare delays in the transmission with the delay on the connectors, which could be, within nanoseconds, I don't think that any delay on mechanical wire connectors is significant for the system and create significant jitter for the whole system. What we are talking about is 1 gigabit network. So a byte is transferred within 1 nanosecond, just 10 nanoseconds on the network. So delay on the connector maybe a byte or two, while the cycle time and jitter is an order of magnitude higher than that.
Sure. Okay. Thanks, Alex. Let's take another question now. We've got one here from Alejandro Apacio. He would like to know, how does the system detect a grandmaster failure if, like you said, modifying the time is part of their job, pushing it forward or delaying it? I don't know if anyone wants to take that one, Alex or Austin, or you, Eric.
Yeah, I could take that one. So, I mean, it really depends on what type of failure occurs in the grandmaster. If it was complete failure, then our system that would have been acting as a PTP slave would then, realize a grandmaster is no longer on the network, and our system would go through, it's called the best master clock algorithm. And our system as well could become the grandmaster on a network. But if you're talking about, grandmaster failure that completely loses, synchronization to, say, GPS, and its time shifts, I don't think there's really any way to, at least within PTP, to recognize that. Certainly knowing how much time jump there is, PTP tries to handle it in different ways, but it might be up to the application level to check the PTP hardware clock and check to see how much the time has changed. And if it's changed by, an inordinate amount, then certainly that would flag to say that there's an issue with that grandmaster.
Great, thanks, Austin. I've got a question here. We'll move on to this question here from Youssef Elamari. He is quite seems quite a straightforward question. Who's using TSN now instead of ARINC and MIL standard and other standards? Anyone like to take that?
Who's using go ahead. Sorry.
Yeah, so I could jump in. Our experience is the U.S. military is looking at TSN for their next generation helicopters, as well as for their next generation ground vehicles. So that is becoming the backbone, the digital backbone on these systems. And I'm believe it's meant to replace systems like CAN, systems like Mil Standard 1553, as well as ARINC 664.
Great. Okay, and that's due to some of the complexity of these new systems, right? As I was saying, as we were talking about just briefly after the presentation. That's
due to complexity. I think they're also trying to increase the capability and also decrease the cost.
Right.
One thing what is good about using TSN relies on commercial off-the-shelf standards and relies onto the equipment which is widely used, Ethernet traffic. And yeah, as Erik said, one of the things is to rely as much of the cost technology as possible, so decreasing the cost. And the second thing that Ethernet right now, people are talking about 1 gigabit networks and 2.5 gigabit networks over fiber. So in the future, once more devices are on the market, we are talking increasing the traffic on the network to multi-gigabit, say 10 gigabit within the vehicle, or 25 gigabit fiber within the vehicle. And also you see the fact that you get so much bandwidth compared to MIL 1553 or CAN, or even ARINC 664, which is only 100 megabit per second network, gives you ability to combine all the traffic into a single network. So it will help you with both wiring and the weight inside the vehicle, as well as design. So you can design the system and set up all requirements and timing across the whole aircraft, rather than deal with different subset of the communication equipment, like one is 1553 bus, one is CAN bus, or ARINC 429 bus. So it basically let you centralize development into one ICD document and help with develop more robust solution.
Okay, so you see this TSN replacing these existing networking methods that we're talking about at the moment eventually? I mean, entirely or partially, or is it?
Well, the MIL 1553 standard was developed, as I could remember, in 1977. So it's 1553B. So it has a quite long life and is still going strong. So I don't expect TSN to replace everything at the same time. I would rather see TSN will be introduced into the new vehicles rather than replacing retrofitting old vehicles. But I know that many Avionics companies are now working on implementation TSN for their future generation of devices.
Okay, interesting. It's the way things are heading. Okay, let's take another question. This one's from Simon Bock. He would like to know, have you guys ever participated in a TSN plug fest? I'm not quite sure what that is. Have you tested your TSN hardware with other vendors? If so, who? Who would like to lead with that one? So
I'm not familiar with too many TSN plug fests. We certainly have tested our hardware, or our hardware is used in networks that have TSN compliant switches, and is communicating with other TSN compliant hardware. I don't have all the model numbers offhand right now, but yes, it's certainly in use as we speak.
You know, we did check our TSN with Net Time Logic Evaluation Board, but we have not participated with actual plug fest. It's in our plans.
Okay.
Yeah.
Great. Thank you. So there's another question here from some of these pronunciations are tough today, so you'll have to forgive me, guys. But Balaji MK would like to know what is the computation load for the scheduler in TSN versus ARINC 664? Computational load. Anyone want to take that?
Yeah, that's a big difference. In ARINC 664, certainly you can implement this ARINC 664 in FPGA, but most companies did implement ARINC 664 with real-time operating system because the gap which they need to define between packets and bag is pretty large. Within the smallest one is 1 millisecond, so a CPU can handle that. And by writing, we do have, I wrote a ARINC 664 product myself, so the computational load on a ARINC 664 scheduler is pretty significant. If you look into TSN implementation, TSN cannot really be implemented at the CPU level. It has to be implemented on FPGA or ASIC. So basically implementing this in the hardware. And by doing this, you actually offload CPU from handling packet schedules and handling both tasks and leaky bucket as schedulers. So you move this computation power required for scheduling from the CPU to the hardware. So that's one of the advantage of TSN implementation.
Great, thanks, Alex. Anything to add? Anyone there, Austin or Eric? Or... No, sounded pretty cool.
Yeah, no. Basically, to break it down, ARINC 664 is handled on the processor, so there's a lot more processor load than TSN. TSN's handled down in the hardware. So.
Okay.
And as Eric showed in the presentation, TSN only defines first 3 layers of the ISA network stack, so it doesn't deal with the content of the packet. Your user application deals with content, and certainly that's whatever load you need to put in your user application running on the CPU. The only part which TSN deals is delivery of the packet at the time, and maintaining your jitter and your latency over the network.
Great. Okay, thanks. Let's move on. Look, I've got a couple of questions here from existing members and some from some new names here. Let's take this one from Alejandro Aparicio first. He would like to know as well how TSN compares with time-triggered Ethernet. If anyone want to chime in there?
TSN is you can compare 802.1 QBV with time-triggered Ethernet. Basically, it has the same concept to transmit a packet on time. But realistically, they certainly looked when they developed TSN and in the concept of time-triggered Ethernet. And my opinion that they expanded the number of protocols to cover more different requirements for the Ethernet. The first thing what is different that TSN allows you to have, to manage best effort traffic, basically, for example, downloading a map into the Avionics device as on the same network as well as time critical traffic. That's a difference. And also TSN includes FRAIR, so basically redundancy, and it includes preemption of the lower priority traffic, which is not in the time-triggered Ethernet. So I would say that TSN is just, it took a concept from TTE and expanded some. That's my take on it.
Okay. Great. Okay, thanks. I've got a question here from Alan Hagen. But it says it's not really a question, Alan. If you want to add on to it, Alan's just asking, he's stating today we are discussing vehicle-centric networking only. I don't know if that makes sense to you guys, or if is there another type of networking that Alan would like to discuss. If he wants to resubmit a question, that's fine. No,
I mean,
okay.
Yeah, primarily we were talking in context of aerospace systems. Yes, vehicle control systems. Yes.
Okay. So there's a question here from a person called Richard Collins. He would like to know what scheduling tool that you use. So, Is it quite general, or?
Yeah, I mean, I guess, so if we're talking about TSN and we're talking about the time-aware scheduler, I guess in terms of like configuring the network, all of our configuration works through an XML file. And basically what we've done there is we've tried to take, they have Yang models to define the network. And with a Yang model, you can create kind of a skeleton XML. So we take that skeleton XML file and we can, generate a schedule. And what you do is you specify the overall schedule time, and then you break down the overall schedule time into each cycle that you want to send. And then within each cycle, you can say, which priorities are available for sending and for how long. I'm not sure if that kind of answers the question. I mean, really, overall, there needs to be an understanding of the network to know how to configure the scheduler. But for configuring, the scheduler that we use, it's available through XML.
Okay, thanks, Austin. I'll pose another question here. It's one from Florian Myrtle again. He would like to know if your system supports reporting of TSN and network-related parameters such as latency, scheduler status, bandwidth, packet drops, warnings, and alarms, etc. Does that make sense to someone on the panel?
It does. Some of it is kind of higher level than just TSN because TSN is really, it's not defining what's in the packet. So the warnings or alarms, I'm not sure if that, is related to a data value or if those warning or alarms are related to maybe the latency. But I would say for the other questions for latency, bandwidth, we don't have any way currently to read it. We can read the scheduler status, so you can see, how it's been configured and what it's currently configured as. But for the other parameters, I think it would take a little more knowing, kind of embedding the timestamp within a packet to know when it was sent compared to when it was actually received.
Great, thanks for that, Austin. I'll take another question now. This one here is from Yusuf Alamari again. He would like to know if TSN can also be used as a replacement for ARIC 818, which is used for video transmission.
I think with providing sufficient bandwidth, yes.
Great.
Because 818 has quite the bandwidth, and then you can transmit this video data over the regular TSN network. And that's one of the advantages of TSN, and one of the goals is to combine everything into one network. Like, for example, the AV protocol was initially developed for automotive, for infotainment system inside the vehicles, automotive vehicles, but it certainly there are conversations that it's going to be part of .1TP profile, and it will allow transferring video. It all really depends on the bandwidth, because I can hear that people are looking into much higher speed networks than 1 gigabit networks. They say 10 gigabit over copper and 25 gigabit over fiber networks, so much faster networks. And again, since it's all scheduling, all timing, and all packet handling is done in the hardware, it is possible to do that compared to slower scheduling on the CPU inside real-time operating system.
Okay, thank you. I have a question. I appreciate I'm rattling through this quite quickly, but we're getting a lot of questions in, so I appreciate the brief answers as well, guys. But there's a question here from Stuart Watson. He's got two in one actually, and it's kind of linked to that. He'd like to know how what can be recorded on board during a flight test, and second, he'd like to know. Oh, I've just lost that question. Oh, there it is. He'd like to know what can be transmitted over telemetry back to a range.
It's a good question. TSN doesn't really define what data you transmit.
Right.
Only defines delivery of the data on time. So if you need to transmit telemetry, it depends what telemetry system you are using, but usually you can have a device which will take Ethernet input. You packetize your data in a proper standard. Like using, for example, IEEE chapter 10, chapter 11, packetizing data, and then you feed into your telemetry device on time. The TSN guarantees delivery on time, but then your device will need to send over radio link back to the Earth, and then you need to take this data and display it or decode or use a recorder for this data, all of that together.
Okay, thanks, Alex. So I have another one here from Alejandro. I've got a couple from Alejandro actually. He's on fire today. So first one is he'd like to know how TSN deals with new end systems added on the fly. Is that possible, or does it need to be reconfigured via the XML file?
It does need to be reconfigured because you need to configure all switches for all VLANs ahead of time, ahead of the starting network. If the device is already configured and it gets connected during the operation, it will be certainly recognized. Otherwise, I think most likely switches won't let this data to the egress ports of the switches.
But that certainly opens up a good additional failure mode that could be added to a verification system. Is put on a rogue endpoint, so to speak, and see what happens.
Okay, Alejandro, he would also like to know if there is MAC policing or IP policing in the TSN at switch level. Got to think about that one, or?
Yeah.
Yeah, I mean, I guess we don't really have a switch that we're implementing. We're an end system. So I think it's most likely probably MAC policing, because when we think of preemption, that's actually at the MAC level that occurs. In that, basically the preemption protocol supports what's called an express MAC, and that will allow packets to preempt basically best effort traffic. And that has to happen at the MAC level. So I don't know if that answers the question, but really, yeah, it's got to have some sort of MAC awareness and definitely knowing which packets it can preempt. And again, that's at the MAC level.
Good stuff. All right. I'll put a last call out for questions now. I think I'll echo what other people seem to be posting now, which is that it's an interesting discussion, and everyone seems very engaged in TSN, which is great to see. So if anyone's got any questions, now's the time. We've got about 10 minutes left on the platform before we get ejected. So. It doesn't look like it. So I don't know if you want to sum up, Erik or Alex or Austin, and just maybe what if people still watching, what you'd like your key takeaways to be here today.
Well, I would certainly like to thank everybody for participating, because I certainly hope it would be a nice back and forth like what's happening now. We are also trying to learn about TSN systems and what some of the verification needs are. And we've certainly seen some issues we've seen with TSN and endpoints, as far as, do those endpoints actually have both streams coming in, or has the replicated streams already been consolidated before it gets there, and what that does to your systems. Got a couple more questions I see coming in.
Yeah, it shook people out. So Stuart would like to know if there's any other users in the UK.
I'm sure there are.
Okay, and there's one here from Alan as well. Alan, who'd like to know if I have a 10 gigabyte network, do I need TSN?
Do you need TSN? Well, remember what TSN is for deterministic traffic control. So the real question is, what are you doing with your 10 gigabit network?
Right. Okay. Cool. All right. Alex or Austin, do you want to say anything before we say goodbye to everyone?
Well, I would like, first of all, thanks for all participants in this webinar, and I would like to say the first thing is that TSN profile for Avionics devices is not yet fully defined. We expect it to be defined by the end of next year, beginning of the 2024. This is one thing. So we are working toward implementation, and it looks like TSN is the way for real-time networks to actually use as a new way, and it will be getting more and more acceptance on the down the road. This is the first thing I would like to tell. The second thing, we are, as an organization, as a company, we are always listening to the needs of our customers, and certainly we would like to listen from you. What are your requirements for testing TSN networks, so we can work on it and integrate it into our product to fulfill your requests and your needs, to make testing easier and more affordable, I would say.
Great, thanks, Alex. On that theme, actually, just before I go to Austin for the last time, there's a late statement here. He's saying Simon Fock, who wants to point out that for them, interoperability is important, not just verification.
Mm-hmm.
So is that the kind of feedback you guys are looking for? Then is it?
Yeah,
somewhat. Go ahead, Austin. Sorry.
Okay. Yeah. I mean, that's kind of the idea of the protocols within TSN as well. Is yes, to implement TSN, everything on the network, every switch, and then any end systems that you want deterministic behavior from do need to support the TSN protocols. However, you can have normal Ethernet traffic on that same system, and that Ethernet traffic will be just basically labeled as best effort traffic. So in terms of, if you have a system that there's parts of it that you need deterministic traffic and other parts you want to leave with older, just standard Ethernet, that will work over TSN.
Great. Okay. Thanks, Austin. So I'll finish up there, just again by thanking everyone for their participation and attention today. I'm sure Erik and Alex and Austin, if you've got any questions or anything you do want to discuss in this public forum, then we'll gladly talk to you after the event. The recording of this will be available afterwards. You'll be emailed a link to send you to it, and anyone that hasn't seen it can register for the next few weeks and watch it via the Big Marker platform. After that, it will be uploaded onto the Aerospace Testing International website to review. So once again, thank you all. Thank you, Erik, and thank you, Alex and Austin, for your time. Thanks for your attention, everyone. Have a good one. Cheers.
Thank you all.
Thank you.